Yeah. Yeah. Okay. Yeah. I'm also having this YouTube link in front of me. Yeah. 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 I will have. No one has joined yet, right? Sunita, in reply to the questions in YouTube, I can speak also, right? They would be able to hear. Okay. Okay. Uh, yeah, just I'll tell you. Come in. So basically, what you do is that let me just switch off the camera. It's quite disturbing. Okay. So what you do is that you calculate, thinking that there is something called ether. So you calculate the time taken for the light to go from the source and getting reflected via the reflector and coming back to the detector. So that's one time. And then you have, so there's a splitter, right? The splitter is, uh, so there's one beam that moves vertically upwards and one passes through. And then there are two mirrors that are kept at 90 degrees. And you calculate the time through which, they would be coming back to this thing. And now what you do is that because you have sort of assumed that the light travels through material medium, so they'll have different velocities if you move along the direction of the light, speed of light, and not in the direction that is in a direction opposite to that. So the speeds will be different and the time taken would be different. And then you rotate the instrument by 90 degree, the whole setup by 90 degree, and again calculate that. Okay. So these two time difference will give you the fringe to shift. The calculations are shown in the class, the detailed calculations. So you should have a look at the calculations and they would be there. Any other question? Yes, any question? question you have to ask quickly. Minute. And if we don't get any question, we could wind up earlier than that. Um, yeah. So yes, Hamiltonian mechanics they are easier to solve than Lagrangian, but you should remember that Lagrangian is a function of q dot uh, not t implicitly, whereas the Hamiltonian is a function of p and q. So Lagrangian is a function of generalized coordinates and generalized velocity, whereas Hamiltonian is purely a function of q and p, that is coordinate and momentum. It is true that it looks like they are first order equation, but you have to first identify the coordinates, the generalized coordinates and the generalized momentum. And then from there, you have to calculate the Hamiltonian by taking a PQ dot minus L and so on. And then you have to use the Hamilton's, equation of motion. So even if it looks like that they are simpler, they are more actually, it involves more work than just solving Lagrangian equations. Uh, yeah, how O sees O prime, which means that there are two origins. One origin is at O, and the other origin is at O prime. O prime is moving with a speed v with respect to O in a certain direction. So how somebody who's standing or sitting at O is seeing the other person who's sitting at the origin of the moving coordinate system, how it sees. So that's what it means by how O sees O prime. That's what it means. That is how they are related, all the x, y, z, and time, all these coordinates, four coordinates, three space coordinates, and one time coordinate. How these coordinates are related. That's what it means by how O sees right. Anything else? Uh, how are the how are the unitless? The generalized coordinates take into account all the constraints of the problem. So if two particles are moving in a plane and they are connected by some rod, you would think that there are four generalized coordinates there in a plane. But there are, I mean, x1, y1, and x2, y2 for each one of them. But if they are connected by a rod, which means all these, their relative difference always remains the same. So, which means that there is one constraint condition. So, the generalized coordinates, as opposed to the normal coordinates, they take into account um, this, the constraint conditions. Right. So significance of action is that action is a word which is used, LDT is called as the action density. So integral of LDT is called as the action. Now the significance of action is that it is Newton's laws do not specify the path that a particle takes. It simply tells you that under the application of force, the particle goes from some x1 t1 to x2 t2. However, if you if you this Lagrange's equation of motion tells you that which path do they take, exactly which path, and in which the action would be extremum. That is, delta of that integral of LDT is equal to zero. So that's the significance of the action. So the Lagrange's equation of motion, even though they would coincide with Newton's laws, however, they exactly specify the path along which the particle has traveled. So that's the significance. Anything else? Yeah, I mean, a generalized force and not necessarily have the dimension of force. Like generalized momentum may not may not have a dimension of momentum. It can have dimension of angular momentum and so on and so forth. So in that way, the generalized force also, which takes into account all the constraint condition, it may not necessarily have the dimension of force. Which means that normal force is given by mass into, MLT minus 2. So this constraint condition may actually change the unit from MLT to the power minus 2 to something else. However, most of the cases, the generalized force is taken to be equal to zero, and we have considered equilibrium. situations. Yeah. So yeah, right. So this is the D'Alembert's principle. Um, I have to. Can you write to me? I will look for an example. There are many examples actually. Like for example, any force that acts in order to cause a displacement which is perpendicular to it, which means that your work done is equal to F dot ds. So F and ds, that is the displacement, is perpendicular, then F dot ds will be equal to 0. So if your generalized force has this behavior, then of course then it does no work. Okay. So this is called as the D'Alembert's principle. Yes. Yes. Correct. When we derive principle of virtual work. Correct. Absolutely. Just go through those lectures carefully, and if you have any questions, you could email me. Mm, yes, I mean, yeah. So let me. I mean, if you know, when you when you can express the constraint condition as as an equation, then it is called as holonomic constraint. Okay. Um, so suppose a particle is moving on the surface. So a small ball is rolling on the surface of a sphere. Or, for example, a mass spring system, for example. So these are a mass spring. So the mass can move, relative to the where the spring is fixed at one end. Um, so this is like an equation that you can refer to as. So in the non-holonomic, there is no equation. Okay. So it sort of, there is no constraint with regard to some coordinates or with regard to some that it is being tied, the two masses are being tied, etc., etc. Um, so, so that's a non-holonomic thing which cannot be expressed in some equation form. Say the equation is, say, g of q. Q is the generalized coordinate, and t, which is equal to 0. So that's the equation that we are talking about. Um, so, and what could be an example of non-holonomic constraint? Suppose when a small sphere is or small pebble is moving over a large sphere, uh, and it's say rolling without slipping. Um, the velocity, or when a cycle tire is moving, so the contact velocity remains the same, or rather the velocity at the contact point remains the same. This cannot be expressed as an equation. Even though it's a constraint, it's not a holonomic constraint. That is what I'm trying to say. Yeah, I mean, see some examples. There are many examples. Basically, the one you can express as a constraint equation is called as a holonomic, and that you cannot explain as constraint equation is called non-holonomic. I gave you some examples. So maybe a simple pendulum. So the pendulum, the bob of the pendulum is always connected to the rod or to the string. Okay. For Lagrangian, you can, so Goldstein is a good book. Morin is a good book, Morin. And for STR, of course, you have Resnick and AP French. These are very good books on STR. In fact, you asked a good question. In fact, never, only relying on notes, I present my viewpoint. If you need to have more clarity in terms of more examples, since the time is fixed, so the number of examples that can be given or number of problems that can be discussed is limited. But if you want to know more, then of course you have to, on that particular topic, you may have to, talk about or rather read some books. Yeah, so I gave you names of the books. Any other question? Yeah, yeah, of course. I mean, the question what you have to do is that you have to identify the generalized coordinates and then form the kinetic energy and the potential energy. The form of the potential energy would be given because it will be, just give me a moment. Just a moment. Yes, sorry about this. Yeah. So basically, you'll have to, you have to, all these generalized coordinates, you have to identify that what are the coordinates of the problem, and then use the conditions that are given and reduce the number of coordinates required. That will be the generalized coordinates. And after you get the generalized coordinates, you form the kinetic energy as like half m q1 dot square plus q2 dot square and so on and so forth, depending on how many coordinates you have, generalized coordinate. And from that, you also form V. Um, yeah, but L equal to T minus V, you have to form from the knowledge of the generalized coordinates. So T is equal to half mq dot square, and V is equal to whatever V that is given, which is a function of Q, only Q. Okay. And then you take a difference between the two, that will be the Lagrangian, and then you use the dt of del L del Q dot minus del L del Q equal to 0. Depending on, this is generalized coordinate. If you have two, then you have Q1 and Q2, so you have separate equations and so on. That's what you have to do. Any other question? We have very limited time now. So if you do not have any questions, we'll wind up in 5 minutes. Yeah, there are many book, there are a lot of books actually. I mean, whether you have solved problems, then you have to look at Griner. Griner usually solves a lot of problems. Or um, a large number of problems I have also given, not large, but at least some problems. Um, so you can look at, try to solve these problems, such as, the um, central force problem, etc., or small oscillations, or these Lagrange's, usual Lagrange's equations from Goldstein. If you can solve them, you're surely going to get good score in net gate. Yeah. So yeah, yeah, the same question. I mean, basically it's what I'm saying is that um, I, there is also a book by Morin, Morin, and Greiner. These two are good classical mechanics books. I mean, Greiner usually has in all subjects. Goldstein, I would say, Morin and Goldstein, these are good books. Morin has a number of problems solved. Okay, so these are guide, you can use them as guide. Here about a few minutes left, of course. So if you have any questions, please do ask. Thank you. Thank you, Vishwajit Singh. Sunita, are you there? Yeah, I think that's all. Basically, he was the only one asking questions. There was another one, but I think that so I guess we can wind up now. It's more than 50 minutes. Okay. Is that okay if I wind up, Vishwajit? Yeah. All right then. We'll have more sessions, 2 more sessions to come by. Okay. All right then. Sunita, do you want me to stay over? Do you want me to stay till 5:50? What I'm saying is that do you want me to stay till 5:15 or we can wind up now? Yeah. Okay. Oh, okay. All the way. Okay. Thank you. Thank you. Thanks to all the listeners. Okay. Bye bye.